Swarm intelligence is fascinating, isn't it? Especially when applied to something like portfolio optimization. It's like, watching a flock of birds finding the best feeding spot, but for stocks.
Exactly. This paper, A Survey of Swarm Intelligence for Portfolio Optimization, really digs into how these nature-inspired algorithms are shaking things up in the finance world.
It's a timely review too, covering publications from 2006 to 2017. A lot has happened since then, but this lays the groundwork,
Oh, absolutely. It tackles the core of portfolio optimization, managing risk versus return. And, as the paper highlights, it's a tough computational problem. NP-hard, they call it.
Which is why swarm intelligence is so appealing. Algorithms like particle swarm optimization, or PSO, and artificial bee colony, ABC, offer clever ways to navigate this complexity. They're like, swarms, exploring the market for the best investment combinations.
Right. The paper goes through all the main portfolio optimization models, starting with the classic mean variance model by Markowitz. It's kind of the granddaddy of them all, huh?
Yeah, though it gets some criticism. It assumes things like a normal distribution of returns, which isn't always realistic. So, they explore other models too, like value at risk, or VAR, and conditional value at risk, CVAR.
It's about capturing different aspects of risk, getting a more nuanced picture, right? And then there are the real-world constraints, things like transaction costs and limits on how many different stocks you can hold.
Yeah, the nitty-gritty. It's not just theoretical. Makes it more complex. So, the paper dives into how these swarm intelligence algorithms handle those constraints. Things like repair procedures, penalty functions, it's all about finding feasible solutions that meet real-world limitations.
I see. And they compare different algorithms, right? Using benchmark datasets.
Exactly. They look at things like how close the algorithm gets to the optimal solution, how fast it converges, and the diversity of solutions. Because, you don't want all your eggs in one basket, even with a swarm.
Makes sense. It's not just about finding a good solution, but a range of them. So, what are some of the key takeaways? Like, where's the field headed?
Well, they point to a few interesting directions. One is developing more advanced hybrid algorithms, combining the strengths of different swarm intelligence methods. Like, maybe the exploration power of ABC with the exploitation of, say, Firefly algorithm.
Kind of like creating a super swarm.
Exactly. And also, more work on multi-objective optimization. Looking at risk and return simultaneously, not just one or the other. And, of course, better constraint handling. Making the algorithms even more practical for real-world use.
So, mimicking nature to master the market. That's really at the heart of it, isn't it?
So, digging deeper into these real-world portfolio constraints, right? It's not just about picking stocks, it's about the practicalities.
Yeah, the nitty-gritty. Like, you can't buy everything in the index. So, cardinality constraints, limiting how many stocks you hold, that's key.
Totally. And transaction costs. Brokerage fees, taxes, all that. Gotta factor that in.
Definitely. And the paper mentions transaction lots, too. Can't buy fractions of shares, usually. So rounding to the nearest whole unit, another wrinkle.
Right. And those boundary constraints? Setting minimum and maximum investment levels. That's practical too.
It is. Keeps you from getting stuck with tiny, illiquid positions. Or over-concentrated in a single stock.
Exactly. The paper summarizes these constraints nicely in Table 2. A handy reference.
It is, yeah. And Figure 3 shows how often these constraints pop up in the swarm intelligence literature. Boundary and cardinality constraints seem to be the most popular. Oh.
Makes sense, right? They're the most fundamental, I guess. Closest to the real-world problems investors face.
I see. So then, on to the methods for portfolio optimization. The paper talks about exact and approximation approaches.
Right. Exact methods work great for simple, unconstrained problems, but they struggle with those real-world constraints.
especially cardinality constraints. Makes the problem NP-hard. So, approximation techniques come into play. Like machine learning and metaheuristics.
Yeah. Though, metaheuristics seem to be the more common approach in this field.
Within metaheuristics, you have single solution and population-based methods. Single solution methods are faster, but population-based offer more exploration, right?
Exactly. And within population-based, you have evolutionary algorithms and swarm intelligence.
Evolutionary algorithms mimic natural selection, while swarm intelligence, well, it's all about the collective behavior of a swarm, right? Like bees or birds.
Precisely. Sharing information, exploring the search space together. And the paper dives into the specifics of these swarm algorithms.
So, in this survey, they looked at publications from 2006 to 2017, right? What were the most popular swarm algorithms for portfolio optimization?
Well, particle swarm optimization, or PSO, was the clear winner, at 63%. Followed by artificial bee colony, ABC, at 16%. Then a few others, like bacterial foraging, firefly algorithm, but much less frequently used.
Interesting. And they're all about balancing exploration and exploitation, right? Finding good solutions but also exploring new possibilities.
Absolutely. Table 3 breaks down each algorithm, its inspiration, how it handles exploration and exploitation. A good overview.
It is. And then Table 4 pulls it all together, right? Shows which algorithms are used with which portfolio optimization models and constraints. Really useful.
So, we were talking about these swarm intelligence algorithms, right? PSO, ABC, how they're used in portfolio optimization.
Yeah, and the paper goes deep into the specifics of each algorithm. Like, with PSO, it all starts with the velocity update equation.
Right, that's the heart of PSO. How particles move through the search space, trying to find the best portfolio.
And most researchers stick to the original formulation, with the inertia weight and the cognitive and social learning factors.
Yeah, but there are some interesting variations. Like, velocity limiting, where you set boundaries on how fast a particle can move.
Oh. To keep the search more focused.
Exactly. And then there's the constriction factor approach, adding another parameter to fine-tune the velocity updates. Makes it more precise.
I see. So, like, different ways of controlling the swarm's movement, making it more efficient.
Right. And some researchers use adaptive parameters, changing the values during the optimization process. To balance exploration and exploitation.
So it's not just a fixed set of parameters, it can evolve, kind of.
Exactly. And, some even incorporate ideas from other algorithms, like genetic algorithms or simulated annealing, to enhance PSO's performance.
Creating these hybrid algorithms? Like, adding a mutation operator from GA to introduce more diversity. Or using SA to escape local optima.
Precisely. It's all about finding the right balance, right? Exploration, exploitation, diversity, convergence speed. It's complex.
Definitely. And then there's ABC, the artificial bee colony algorithm. Inspired by, well, bees.
Yeah, employed bees, onlooker bees, scout bees. Each with a specific role in finding the best nectar sources, which represent good portfolios.
And it seems like ABC was first applied to portfolio optimization by Hongmei et al. Back in 2009.
Yeah, they compared it to genetic algorithms and found that ABC was faster and produced better solutions.
Interesting. So, two very different approaches, both inspired by nature, both tackling this complex problem of portfolio optimization.
So, we were discussing these swarm algorithms, and the paper really dives into ABC, artificial bee colony, right?
Yeah, lots of interesting research there. Like Chen et al. In 2012, 2013, they compared ABC to VNS, SA, TS, and found ABC came out on top for diversity, convergence, and effectiveness.
Right? And Wang et al., they saw similar results, comparing ABC with GA, TS, SA, and PSO.
So, ABC seems to be holding its own against these other algorithms.
Definitely. Though there's always room for improvement, right? Chen et al. Found that the standard Scout-B generation could hurt solution quality, so they tweaked it to balance exploration and exploitation.
Oh. Makes sense. You need that balance.
Exactly. And Bakanin et al., they looked at constrained portfolio optimization, used ABC with a special constraint handling method, and, again, ABC showed potential compared to GA and FA.
So, ABC is versatile, adaptable.
Yeah. And then there's Suthiwang and Sotanil. They boosted the employed B phase by, get this, taking inspiration from PSO. Using global best info to guide the search.
Interesting. A little cross-pollination between algorithms.
Exactly. And Gu in 2015, Kumar and Mishra in 2017, Kalesai et al., also in 2017, they all proposed enhanced ABC algorithms, adding their own twists, testing on benchmark datasets. It's a vibrant area of research.
It is. Table 8 lays it all out nicely. The different tweaks, the parameters, the contributions, it's a good summary.
Totally. Like, how they set the number of food sources, sometimes fixed, sometimes adjusted based on the problem size. Same with those other parameters, like limit, for the Scout Bs.
Yeah. It's all about fine-tuning, right? Getting the most out of the algorithm.
Exactly. And then the paper moves on to other swarm algorithms, beyond bees. Like, ants.
Ant colony optimization, ACO. Inspired by how ants use pheromones to find the shortest path.
Right. But ACO is usually for discrete problems, so for portfolio optimization, you need a continuous version, like ACOR.
And they've compared ACOR with PSO, right? With mixed results. Sometimes ACOR is better, sometimes PSO.
Yeah, it depends on the specific portfolio, the scale of the problem. Then there's bacterial foraging optimization, BFO, mimicking how bacteria forage for food.
Right. Cao and Cheng found BFO outperform GA, TS, SA, and PSO. And then others built on that work, refining BFO, improving the balance between global and local search.
It's a constant evolution. And then there's the Firefly algorithm, FA, based on how fireflies flash.
Bakanin and Tuba and Bakanin, they've done a lot of work with FA, showing it can be a strong contender, especially with some enhancements.
Yeah. And then the paper gets into hybrid algorithms, combining the strengths of different approaches. Like PSO with SA, GA with PSO, even ABC with FA.
Taking the best of both worlds, right? Like, combining BAT algorithm, with ABC. BA is good at intensification, but ABC helps with diversification.
Precisely. And finally, multi-objective algorithms. Because portfolio optimization isn't just about one thing, it's about balancing risk and return. So, we were talking about multi-objective algorithms for portfolio optimization, right? And the paper mentions some interesting comparisons.
Yeah, like this NSMOPSO. They compared it to a bunch of other algorithms, single objective and multi-objective. GA, TS, SA, PSO, even PESA2, SPEA2, NSGA2, and regular MOPSO.
Right? And the results? NSMOPSO shows some real potential, especially if you combine it with advanced local search operators. Oh?
Yeah. Sounds promising. And then Babi et al., they looked at the efficient frontiers, how they can be non-smooth or discontinuous because of things like VAR and cardinality constraints.
Makes sense. Those constraints add complexity.
So, they proposed two MOPSO variants and, they outperformed NSGA2 and SPEA2, especially in finding those non-dominated solutions. Interesting.
It is. And then Kumar and Mishra, they developed this MCABC, a multi-objective covariance-based ABC algorithm.
Right, using covariance principles to speed up convergence. Pretty clever.
Yeah, it seems to have real potential for real-world portfolio management.
So, moving on to implementation platforms, the paper breaks down which programming languages are most popular for coding these swarm algorithms.
Right. C++, C#, Java, MATLAB, though surprisingly, almost half the studies didn't specify which platform they used.
Interesting. But of those that did specify, MATLAB seems to be the favorite, followed by C++. Oh.
Yeah, and then Table 10 gives a detailed breakdown of which algorithms were used with which programming language and dataset.
Right. A handy reference. So, on to constraint handling. This is crucial for real-world portfolio optimization, right?
Absolutely. The paper mentions repair procedures, penalty functions, and Deb et al.'s strategy. Though, again, a lot of studies didn't specify their method.
Yeah, that's a bit of a gap. But it looks like penalty functions are the most common approach, followed by repair procedures.
Right. And the paper also talks about datasets. Researchers use a mix of real-world stock market data and benchmark datasets from the OR library.
Yeah, the OR library datasets are a good way to compare algorithms on a level playing field.
Definitely. And then, performance measures. How do you actually evaluate these algorithms?
Right. There are a few different metrics. Mean percentage error, median percentage error, variance of return error, even a mean Euclidean distance error.
And for multi-objective problems, there's the diversity metric from Deb et al., measuring how spread out the solutions are. Oh?
Yeah. Because it's not just about finding a good solution, it's about finding a diverse set of them. So, computation time is also a factor, but it's hard to compare directly because of different hardware.
So, we were talking about benchmarking, right? And how it's crucial for comparing these swarm algorithms.
Yeah, a fair comparison needs a reliable hardware benchmark. It's not just about the algorithm, it's the whole ecosystem.
Exactly. And this paper, it dives into all these different swarm algorithms for portfolio optimization. Starting with the Markowitz model, the granddaddy of them all, even with all the, criticisms.
Right, like the assumption of normal distribution of returns, not always realistic. So, they look at other models too, VAR, CVAR.
Yeah, capturing different aspects of risk. And then the real-world constraints, cardinality, transaction costs, lots. It gets complex fast.
It does. NP-hard, they call it. So, approximation techniques like, swarm intelligence come into play. PSO, ABC, those are the popular ones. Oh.
Yeah? PSO being the most used, because it's older? And a good fit for continuous optimization.
Right, no need for transformation. Unlike ACO, ant colony optimization, which is usually for discrete problems.
So you need those continuous versions, like ACOR. And ABC, artificial bee colony, it's younger than PSO, but gaining traction.
Showing some promising results. And then you have BFO, IWO, FA, FWA, all these nature-inspired algorithms.
Each with its own strengths and weaknesses. It's all about balancing exploration and exploitation, right? Finding the best solutions without getting stuck. Oh?
Yeah. So, hybridization comes into play. Combining the best of different algorithms. Like, BA with ABC, or PSO with SA.
Exactly. And multi-objective optimization too. Looking at risk and return simultaneously.
Makes sense. And then the implementation platforms. MATLAB seems to be the favorite, followed by C++. Though, surprisingly, many studies don't specify.
Right. And constraint handling, penalty functions, repair procedures, crucial for real-world applications.
Definitely. And datasets, from real-world markets or the OR library. For a level playing field, right?
Yeah. And performance measures. Mean percentage error, median percentage error, lots of ways to evaluate these algorithms.
And for multi-objective problems, you need diversity metrics. Because it's not just about one solution, it's about a range of them. And of course, computation time, though that's hard to compare fairly without standardized hardware.
So, this list of research papers, it's like a timeline of portfolio optimization, right? From the classics to the cutting edge.
Yeah. Starting with Simon in 97, comparing mean variance with mean absolute deviation. Classic stuff. Oh.
Yeah? Then Jorian in 96, digging into value at risk, VAR. Measuring the risk of VAR. Risk squared, huh?
Right. And Dantzig and Infanger, 93, bringing in multi-stage stochastic linear programming. Getting sophisticated.
Then Najafi and Mashakian, 2015, adding transaction costs to the mix. Multi-stage, mean sum of variance, CVAR, complex.
Definitely. And then Sun et al., 2011, using particle swarm optimization, PSO, for multi-stage portfolio problems. Bringing in the swarms.
Exactly. Then Tan et al., 2014, using bacterial foraging optimization. With neighborhood learning. For dynamic portfolios. Oh?
Yeah. And Woodside Oriaki, Lucas, and Beasley, 2013, tackling rebalancing. With transaction costs and an investment horizon.
Practical stuff. Then Liu and Zhang, 2015, bringing in fuzzy logic. And minimum transaction lots. It's all about the details, right?
Right. And Fernandez and Gomez, 2007, using neural networks. A different approach. Oh.
Yeah? Then Abbas and Haider, 2009, comparing artificial immune systems, AIS, with PSO. For constrained portfolios.
So, lots of different algorithms being tested. And Jiang et al., 2014, using factor models and clustering. For cardinality constrained portfolios.
Right, limiting how many stocks you hold. And Chang et al., 2000, using heuristics for the same problem. Cardinality constraints, tricky.
Definitely. Then Scherf, 2002, exploring local search techniques. For constrained portfolios. Oh.
Yeah? And Bekasoglu et al., 2015, using GRASP. Another heuristic. For, you guessed it, cardinality constrained portfolios.
So, lots of focus on that specific constraint. And Holland, 75, laying the groundwork for genetic algorithms. A classic.
Then Ergot et al., 2004, using a multi-criteria decision-making, MCDM, approach. Bringing in multiple objectives. Oh?
Yeah. And Ponsik et al., 2013, surveying multi-objective evolutionary algorithms. For portfolio optimization and other financial applications. Broadening the scope.
So, this survey of swarm intelligence for portfolio optimization, it's pretty comprehensive, right? Covers a lot of ground.
Yeah. From 2006 to 2017. A whole ecosystem of algorithms and applications. Oh.
Yeah? And it really highlights how these nature-inspired algorithms are shaking things up in finance. Like, using swarms to pick stocks. It's wild.
It is. Mimicking nature to master the market. And the paper breaks it down nicely, starting with the core problem, balancing risk and return. Oh.
Yeah? Which is tough. Computationally speaking. NP hard, they call it. So, swarm intelligence offers these clever ways to navigate that complexity. Like, exploring the market for the best combinations.
Right. And they cover all the main optimization models. Starting with Markowitz, the granddaddy of them all.
Yeah, though it has its limitations. Assuming normal distribution, which isn't always realistic. So, they explore other models too. VAR, CVAR. Oh?
Yeah. Capturing different aspects of risk. Getting a more nuanced picture. And then the real-world constraints, transaction costs, limits on holdings, the nitty-gritty.
Exactly. Makes it even more complex. So, the paper dives into how these swarm algorithms handle those constraints. Repair procedures, penalty functions. Finding feasible solutions.
Right. And they compare the algorithms using benchmark datasets. Looking at how close they get to the optimal solution, convergence speed, diversity, You don't want all your eggs in one basket, even with a swarm. Oh,
Yeah? It's not just about finding a good solution, it's about finding a range of them. And the paper points to some interesting future directions, like hybrid algorithms, combining the strengths of different methods. Like a superswarm. Oh?
yeah. And multi-objective optimization. Looking at risk and return simultaneously. And better constraint handling, making the algorithms even more practical. So, the paper focuses on several key swarm intelligence methods, right? PSO, ABC. Oh,
Yeah? Particle swarm optimization, artificial bee colony, they're all about balancing exploration and exploitation. Finding good solutions while still exploring new possibilities.
exactly. And they go deep into the specifics of each algorithm. Like with PSO, that velocity update equation, the heart of how particles move through the search space. Oh,
Yeah? And the variations. Velocity limiting, constriction factors, adaptive parameters, all these tweaks to control the swarm's movement, make it more efficient.
right. And ABC, inspired by bees. Employed bees, onlooker bees, scout bees, each with a specific role. Oh,
Yeah? And they've compared ABC to other algorithms, GA, TS, SA, and it often comes out on top. Though there's always room for improvement. Tweaking the scout bee phase, adding PSO elements, it's a vibrant area of research.
it is. And beyond bees, ants. ACO, ant colony optimization, though you need a continuous version like ACOR for portfolio problems. Oh,
Yeah? And bacterial foraging optimization, BFO, mimicking how bacteria search for food. Firefly algorithm, FA, based on how fireflies flash, it's a constant evolution. Oh?
yeah. And then the hybrid algorithms, combining the best of different approaches. Like BA with ABC, or PSO with SA. And multi-objective algorithms, because portfolio optimization isn't just about one thing. Oh,
Yeah? It's about balancing multiple objectives, risk and return. And they discuss implementation platforms, MATLAB, C++, constraint handling, datasets, performance measures, it's all there.
it is. A comprehensive overview. And the list of research papers is like a timeline of the field. From the classics to the cutting edge. A great resource for anyone interested in, well, swarms and stocks.